With the Z-transform under our belt, we're going to turn some time to analyzing systems using the Z-transform. Let's begin by looking at linear time-invariant systems. And we recall that these kinds of systems are characterized by their impulse response, or in some cases, a difference equation. On the left here, we see the symbolic representation of convolution of an input signal x with the impulse response h gives the output signal y. In the Z-transform domain, we know that convolution becomes multiplication, so here we have the Z-transform of the input times the transfer function of the system yields the output Z-transform. We know also from our past experience with the Z-transform that if we evaluate the Z-transform on the unit circle, that leads to something called the frequency response. And in the following, we're going to take the frequency response and we're going to decompose it into its magnitude and phase responses. And we'll spend a lot of time looking at magnitude response and phase response today. So here we are with the Fourier transform version of this Z-transform expression up here where we've evaluated on the unit circle. So this is the Fourier transform of the output signal, Fourier transform of the input signal x times the transfer function, or I'm sorry, the frequency response of the system. And then if we do the polar decomposition of each of these functions, we have the magnitude and the phase of the output. That's equal to the product of the magnitudes of h and x. And then we have e to the j, the sum of the phase responses. The phase response times plus the phase of the input signal. What we can do is equate both sides, equate the magnitudes on both sides of this expression and the phases on both sides of this expression. And when we do that, we'll get the magnitude of the output is the product of the magnitude of the input times the magnitude response of the system. We could express that in dB by saying that the response, the magnitude of the output is equal to the sum of the magnitude response and the magnitude of the input. Notice that in the dB domain, instead of a product, we have a sum. And then also we have a sum of phase responses if we equate phase responses on both sides of this expression. Let's take a closer look at the phase response of the system, denoted angle h of f. In this example taken from our textbook, we see the phase response as a function of frequency. And notice that the units of the phase response are in radians. We also call this the unwrapped phase or sometimes the continuous phase for reasons that I hope will become clear next. When we're doing work on a computer and we do calculations on a computer, we can calculate the phase of a signal or of a system response, but on a computer we're using a function like a 4-quadrant arctangent function, for example, and we know that the range of the arctangent function is going to be bounded between minus pi and pi. So here we have a situation where the continuous phase response of the system lies outside the range minus pi to pi, but when we do calculations on a computer using the arctan function, it's going to always give us the response, the phase response, modulo 2 pi in this interval from minus pi to pi. So if the actual phase response of the system looks as shown here on the top, the response that we would calculate on a computer would be this one shown here in the middle. And the difference between these two, if you were to calculate the difference, it would be a constant, a piecewise constant signal where that gives us the integer multiples of 2 pi that are the differences between these. So you can see that when we move from this frequency to this frequency right here, we get a jump in the principal value of phase. So we're going to define this function called capital arg, which is the principal value. Sometimes I'll refer to that as the wrapped phase. This is what you calculate on a computer. And then the difference between that and the actual continuous phase is this 2 pi times an integer factor. Well, that integer factor is shown down here for the signal, for the phase response in this example. And there's a process that we can perform on a computer called phase unwrapping, where we detect, as we move, as we increase in frequency, we detect jumps in the phase response. And when we detect a jump, we can add or subtract an integer multiple of 2 pi to try and discover a function that appears to be more continuous. So sometimes we call this the continuous phase or the unwrapped phase. And you can, again, on a computer, you can engage in a process called phase unwrapping that takes us from the principal value of phase or the wrapped phase and returns the continuous phase or the unwrapped phase. There is in MATLAB a function for performing this, and it's called unwrap. So when you calculate, when you say angle of a frequency response, for example, it will give you the wrapped phase, and then if you say unwrap, it will calculate, it'll do the best job it can to calculate the continuous phase. Also, there's another function in MATLAB called phase, which does both of those operations together. It calculates the wrapped phase, and then internally it calls the unwrap function. So those are a few things to be aware of. All right, here's an example of the wrapped and unwrapped phase for an actual filter. On the top here, you're seeing the principal value of phase or the wrapped phase. Notice that the values here lie between minus pi and pi. And then if we undergo the phase wrapping process where we look for jumps in the phase response or the wrapped phase and then do the unwrapping by subtracting or adding a multiple of 2 pi, we can recover this continuous phase response. And so we would say or think about this as being the actual phase response of the system, pictured down here on the bottom. Now, after phase response, there's a few things that can be derived from the phase response, and one of these is called the group delay. And it's denoted by tau, and it's a function of frequency, so it's tau of f. And it is equal to the derivative, the negative derivative divided by 2 pi, because we want the units of tau to be in samples. So it's essentially the slope. The group delay is the slope of the phase response. And you can see why we would want to apply this derivative to the unwrapped phase. If we go back to this previous example, I mean, the derivative would get kind of nasty right here at these jumps. So what we do is we phase unwrap to get the smooth continuous phase, and then we calculate the derivative of the continuous phase to obtain this group delay. Well, what does the group delay tell us? Look at this example for just a minute to get a sense of what group delay is talking about. So let's suppose we have a system whose impulse response is a delta of n minus d. So if we convolve with this impulse response, all that's doing is delaying the input signal by d samples. Here we think of d as being an integer value in order for this to make sense. The frequency response, if we calculate the Fourier transform, is e to the minus j2 pi f times d. If we think about the angle or the phase response of the system, that would just be minus 2 pi fd. And then plugging into this derivative definition and calculate the group delay is just d samples. So with that example, we think about tau, or this group delay, as being the amount of delay experienced by a signal as it passes through the system. That certainly is true in this example. In general, but notice that in this example, the phase was a linear function of frequency. What would we do in this case where the phase is nonlinear? How do we understand this and get our head around it? Well, when we have a nonlinear phase function, as you see in this example, suppose this line right here is the phase response of the system, plotted over the frequency axis. Notice here I'm only showing the positive frequencies from 0 out to 1/2, the highest frequency. And in this example, I want to think about the input signal occupying a narrow spectral band. So suppose this blue line here, or this little blue triangle, shows us the Fourier transform of the input signal. And its energy is concentrated in a narrow band of frequencies around this frequency f0. One way we could obtain such a narrow band signal would be by taking a low-pass signal, S of n, and modulating it by a cosine. Remember, when we modulate by cosine, we're going to shift the signal from DC out to the center frequency of the cosine. So S of n, if we looked at its Fourier transform, it would be a little triangle sitting here at the origin. When we modulate by cosine, that shifts that out to the frequency f0. So that's where this narrowband signal x of n comes from, and this is its Fourier transform. Well, let's suppose that our system that we're going to put this narrowband signal into has a phase response that's given by this curve. And let's take out a Taylor series approximation, a first-order Taylor approximation of that phase response about this frequency. If we were to do that, what we would do is we'd have a constant term where we have the phase evaluated at this frequency f0, and then we would have minus, the minus comes in because of the definition of the group delay with a negative sign in it. But then we would have minus 2 pi f minus f0 times the group delay. Here's the derivative evaluated at that frequency. And so you can see that the form of this, the only variable here is f. And so if we look locally around the frequency f0, the phase response appears to look like a line. At least that's true, or that's approximately true, over the band of frequencies where our input signal has energy. So locally, at least, the phase response looks linear, and the slope of that approximately linear phase response is the group delay. Now we can combine terms and take everything that doesn't depend on the frequency f, and we can bring all those terms over and collect those into this term I'm calling phi of f0. And then if we take these two terms and do some Fourier analysis and then bring things back into the time domain, what we would find is that the output of this system, remember, okay, so what's going into the system? We have a signal, a low-pass signal, times a cosine. The output of the system would be equal to, what happens is we modify the magnitude by the magnitude of the frequency response about the point f0, assuming it's, what we're doing here is assuming it's approximately constant over the band of frequencies, so we can just evaluate at the center frequency. And then we have this envelope that we're calling it, being delayed by the group delay at the frequency f0. And then we have the cosine piece, and its phase is modified by this constant from the Taylor expansion. So you can see that what the group delay is doing, what the group delay tells us in general, and again, this is more general than this simple example here where the phase was perfectly linear. But in general, what the group delay does is it tells us how much the envelope of a narrowband component is delayed in time as it passes through the system. Well, why is that useful? That's useful because Broadband signals. Here, remember, the signal that we're looking at in this example is a narrowband little signal. You could think of it almost as a sinusoidal signal whose amplitude fluctuates slowly in time according to the signal S. And okay, so a broadband signal, we can think of a broadband signal as being a sum of narrowband signals with different center frequencies. This is the whole idea of Fourier analysis of signals. We can build up a broadband signal by adding together a whole bunch of narrowband Fourier components. So this is nothing new. And each component, if we have, notice that in this example, in the blue box here, the phase was linear and the group delay was constant. So every component had the same delay. When that happens, we would say that the system, at least from a phase perspective, is distortionless. Every signal component passes through with the same amount of delay. It doesn't matter what the frequency is. Whereas in this little example here with the Taylor expansion, the group delay depended on frequency. So when we have nonlinear phase, or what we're going to have is variable group delay, which means that different frequency components pass through the system with different amounts of delay. So this is kind of an interesting concept, and it's completely a function of the phase response of the system. It has nothing to do with the magnitude response, only phase response. So let's go back to this example that we were looking at before, where here I'm showing the unwrapped version of the phase, and notice that this is definitely not a linear phase system. It's nonlinear phase. And we have points where the slope is very flat, and we have points where the slope is very steep. So when we take the derivative, and that's what I'm showing down below, the group delay, the derivative is going to be very high at these frequencies, and you can see that here in the chart down below. Again, this is an example from our textbook, so I've just copied and pasted these in. But you can see that the group delay is going to be very high at the frequency 0.2 times pi radians per sample. In fact, if we look on the graph here, it looks like at that frequency we have 150 samples of delay, whereas at other frequencies like 0.6 times pi radians per sample, we get almost no delay at all. And then at other frequencies, we're getting something that looks like an advance because the delay is negative. So what's going to happen when you pass signals through this system? Some pass through with no delay. Others pass through with a very large delay, and some pass through with an advance. And so the trouble with nonlinear phase systems is that signal components at different frequencies will pass through with different amounts of delay. So whereas things might be time aligned on the input to a filter like this, when things come out the other end, they might not be time aligned anymore. Let's take a look at an example. Okay, so here we are, same system. On the top now, I'm showing the magnitude response of the system. On the bottom, I'm showing the group delay. What we're going to do now is we're going to pass some cosine signals into this system, and they're going to be at these different frequencies. We're going to pass one through at 0.2, 0.4, and 0.8. And we'll see that the signal at 0.2 is going to experience a slight gain in amplitude, but not much, whereas the signal at 0.4, it will almost double in amplitude, because with the gain of the filter at this point, the magnitude response is 2. Whereas the signal at 0.8 pi will be essentially attenuated and disappear completely because the magnitude response at that point is 0. Now, if we look at the group delay and see what's going to happen, the component at 0.2 pi radians per sample is going to experience 150 samples of delay. 0.4, almost no delay at all. So it'll stay in about the same position at the output as at the input. And again, the signal at 0.8 would normally experience even an advance, but the trouble is the amplitude is going to be set to 0, so we won't even be able to see it at the output. Let's take a look at the signals going in and coming out of this system. Okay, so at the top we see the signal going into the input. We have a high frequency signal. This is the signal component at 0.8. We have a low frequency signal. This is the one at 0.2. And the one in the middle here is a medium mid frequency. This is at 0.4. Let me go back and just remind you. We've got 0.2, 0.4, and 0.8. And the way those signals are arranged in the input is the 0.8, then we have the 0.2 and the 0.4. So let's just look and see what happens to these things in order. Okay, so at 0.8, remember the magnitude response at 0.8 says that signal is not going to appear. It's going to be completely wiped out and attenuated. And if we look at the output signal, which is the lower graph here, we see that that is in fact the case. So this signal completely disappears in the output. Now let's move on to the next one. This is the signal at 0.2. Let's go look this up in the charts on response and see what's going to happen. At 0.2, the magnitude is slightly increased, but not much. What really changes is that we have 150 samples of delay. And then the other signal at 0.4, the mid-frequency, it will have a gain of 2, and it will not be time delayed at all. So let's see what happens. Okay, so here we have 0.2. It looks like it's centered at about, maybe 90-ish samples. So if you add 150 samples, that's going to take the center over to 240. Now the amplitude here is 1, and the amplitude in the output is again about 1. So we see this time delay taking place. The mid-frequency has an amplitude of 1, and it's centered at about 150 samples. And we see that its output is doubled in amplitude as expected from the, as predicted by the magnitude response chart. And the time delay is not much, maybe a sample or 2. And you can see that that's actually what happens here. So isn't it interesting that we have these signals at the input, and the low frequency actually appears in the input, it's before the mid-frequency, but at the output it appears after. So this is what I mean when I say different signal components can experience different amounts of time delay going through this system if the system has a nonlinear phase response. And this one certainly does. So again, where the phase response is steep, you have a high delay, and where it's flat, you have a low delay. It's really an interesting idea that you could make this sort of thing happen. And so in some cases, this might be a desirable property. In other cases, it might be an undesirable property. For right now, we just need to understand it. Now let's go and look back at general linear time invariant systems. So in this case, we've got a difference equation, which is a very general description for a linear time invariant system. And we know it's very simple. Almost by inspection, we can write down a rational transfer function for this system. And you can see the way that that's written down here in the correspondence between the coefficients in the difference equation and the coefficients in this rational function. The coefficients in the numerator polynomial come from the input terms, and the coefficients in the denominator polynomial come from the output terms. Usually we assume that a sub 0 is 1, but in the work here I'm not assuming that. But it can certainly, things can be scaled so that that is the case. Here I'm showing a factorization of the polynomials in the numerator and denominator in terms of the zeros and poles of the system. And then if we evaluate this on the unit circle, we get the frequency response. Now, the frequency response, if we want to look at the magnitude and the phase response, we can just take the magnitude of both sides here to get the magnitude, which we can express either in linear form or in dB. Notice that in the dB form, we're going to sum the contributions due to the zeros and subtract the contributions due to the poles. In terms of the phase response, we're going to do the same thing. we're going to add the contributions due to the zeros and subtract the contributions due to the poles. It does take a little bit of calculus effort to derive the expression at the bottom of the page here, which shows how poles and zeros affect the group delay. And I encourage you to sit down and just take a sheet of paper and attempt this calculation. It's a fair piece of work, as you'll see. So if you don't mind, we'll just take that at face value. Let's go on now and look at phase response for a single pole and single zero. Notice that in every one of these terms, the overall response consists of a contribution due to many zeros and many poles, regardless of which expression we're looking at here. So what it would be worth doing would be to focus our attention and ask, what does the response, the magnitude response and the phase response and the group delay look like for a single zero and for a single pole? Now, as we do this and examine this, what we're going to do is look at the magnitude and phase and group delay for a single zero. And if we want to understand what the corresponding magnitude and phase and group delay would look like for a pole, all we have to do is change the sign and things flip upside down to answer the question. So with that, let's jump in and look at what the magnitude, phase, and group delay look like for a single zero. Okay, so here's a single zero where the zero appears at A, z equal A, which is a complex number, could be anywhere in the complex plane. And if we write this in a different form, we see that this single term contributes a zero at A and a pole at z equals 0 at the origin. And if we evaluate this on the unit circle, and then imagine that we have the polar form for our zero location, we can make some plots. Let's assume that the radius of the pole is 0.9, so this is just inside the unit circle. And then the angle of the zero is at 0, so that would be on the real axis. And then 1/4, that would be on the j-axis. And then 1/2, that would be on the negative real axis. So as we do this, let's take a look at the magnitude response. So the solid line represents the 0, the dashed dot line represents 1/4, and the dashed line represents 1/2. So as the angle of the zero increases from 0, you can see that the response shifts, or the dip in the response shifts from 0 frequency around the unit circle or across the frequency axis to 1/4 and then 1/2 cycles per sample, or this graph shows it in radians per sample. But in general, what we expect to see with a zero is some kind of a reduction in the magnitude response at angles that line up with the angle of the zero. So here we have a reduction in the magnitude response at 0 frequency. And then as we move across in frequency, it goes up to 0 dB or even above 0 dB. The phase response has a similar type behavior. What happens is the phase changes from negative to positive at this frequency. So there's actually a 0 crossing in the phase. But notice also that the phase has its steepest value right there at the given frequency, and so we get a maximum or a minimum, in the group delay at these frequencies. And so this gives a suggestion. If we wanted to design a system that had a particular magnitude response or a particular phase or group delay response, we could place. This would give us an indication of where we should place the zeros to make that response happen. Again, I want to remind you that what do the responses look like for poles? remember, poles are going to just be the negatives of each of these. So for a pole, we would have a peak instead of a null in the magnitude response. The phase response is going to flip the other way around, and so the group delay, instead of being negative, would be positive for a pole inside the unit circle. All right, so in these charts, what we're doing is keeping the radius of the zero fixed and varying the angle. What I want to do next is look at an example. Again, this is from the textbook. But in this example, what we're doing is we're keeping the angle of the zero fixed, and we're varying the radius. So we're moving this from deep within the unit circle with the radius of 1/2 out to 0.7, 0.9, and then 1.0 right on the unit circle. So here what we're doing is moving that zero closer and closer and closer to the unit circle to see what the effect is. So again, because the angle is 1/2, we're going to see a dip at high frequencies. Remember, 1/2 or pi in terms of radians, this is the highest frequency, and that's the angle of our zero. So that's where we would expect to see the response go, plummet down to getting close to 0, or in dB, negative infinity. Notice here, when the zero is far from the unit circle, we have only a mild dip in the response. And then as that zero approaches the unit circle, we get a deeper and deeper notch in the response until finally, when it lies on the unit circle, we get a true null in the response at that frequency. The phase response, we have a similar kind of behavior. As when the zero is far from the unit circle, we get just a mild modification of the phase, and then as it approaches the unit circle, we get a more and more significant phase response. And so what that's going to do is change the group delay more and more dramatically at that frequency. So notice that the group delay is more drastic. The delay is larger as we bring that zero out closer to the unit circle. So again, what would this look like for poles? Again, poles are just going to be the negatives of everything that we see here. So we would see a dramatic increase in the magnitude response at the location of the pole, or at the same angle as the pole, as that pole approaches the unit circle. And then we would see larger and larger delays as that pole approaches the unit circle. Now, what we've looked at so far is the response due to individual zeros and poles. But you can imagine sort of putting these things together as cascades of poles and zeros, and then getting the combined responses. So in this example, the pole zero plot appears at the bottom of the page. We see we have 3 zeros and 3 poles. So these zeros are pulling the response down at the frequencies corresponding to these angles in the complex plane. But the poles are pushing up the response at frequencies corresponding at the corresponding angles. So here at frequency 0, which corresponds to the point right here on the real axis, the point at 1, we're close to some poles, and that's tending to push the response up. We're far away from the zeros, which are pulling the response down. Also, you see that as we get close to poles, the response is going to have more and more a steeper phase, which is going to give us a larger group delay. And then as we come over here close to the poles, or to the zeros, I'm sorry, the delay will actually go, or can go negative. The group delay can go negative, which is in advance. I'm going to add some more, let's see here. Some more details on top of this example here. So notice here that we've, at frequencies that give us points close to the poles on the unit circle, we have poles pushing the response up, And then as we pass through, as we move around the unit circle and increase in frequency, we're going to pass through these zeros. And so at those frequencies, the zeros are pulling the magnitude response down. In general, I mean, this is hand waving. Zeros pull the magnitude response down, and poles push the magnitude response up. If we really want to be technically correct about this, there's a better way to look at this, and that is, and I'd like to use an example to illustrate that idea. So at the top of the page, you see here a difference equation where we have 3 terms in y and then 1 in x. So if we write down the transfer function and then factor the transfer function, we'll get terms that look like this. If we factor out z, if we multiply top and bottom by z squared, we can also write the transfer function as you see here. Then, if we evaluate the transfer function on the unit circle, we'll get an expression that looks like this. We can take the magnitude and study the magnitude of that transfer function, giving the magnitude response, and we can see what's happening. So let's pick a frequency and say z is equal to e to the j2 pi f, the frequency in question. And so what we'd like to do is evaluate the frequency response, the magnitude response, at that frequency f. So I've put a point, a red circle right here on the unit circle, which is the point corresponding to the frequency in question. And this vector v3 points from the origin out to the point in question. And notice that there are 2 zeros at the origin because we have a z squared, and then we have a pair of complex conjugate poles. So this is the pole zero plot for this system. Here are my complex conjugate poles, and then my zeros are here at the origin, represented by 2 circles there. Now, if we look at the form of the transfer function, the magnitude of the transfer function, what we have is, in the denominator, we have the point e to the j2 pi f, which is, again, is the point on the circle, and then we subtract from that the pole location, which is this point right here, x. If you think about what that is in terms of the difference of these 2 complex numbers, or this phasor, that gives us this vector that points from the pole to the unit circle, the point in question. Then if we do the same thing over here, again we have the point on the unit circle subtracted, and then we have subtracted the opposite pole location, the conjugate pole location. That gives us this vector v2. And then in the numerator we have, again, the point on the unit circle in question minus 0. And I've left off the minus 0 because it doesn't change anything. But we should realize that it's there. So if the zeros were not on the origin, we would have to include those effects here inside this magnitude. So we can see that the magnitude response is given by the magnitude of 3 different vectors here. These are, again, the difference vectors, the vectors that point from the poles and the zeros to the point on the unit circle in question. And so if we call these vectors, if I call this vector v3, and this one v1, and this one v2, we see that for any frequency, the magnitude response is the product of the lengths of the zero vectors divided by the product of the lengths of the pole vectors. So what are zero vectors and pole vectors? Those, again, are the vectors that point from the poles in zeros to the point on the unit circle in question. In this example, v3 has a magnitude of 1, so that simplifies as shown here. And that's true for all frequency. But v1 and v2, the magnitude of those vectors changes as we move around the unit circle. And so you have to do the rest of this calculation just sort of mentally in your mind. But what I've included here is a picture of the magnitude response. So for a point at the origin, we have these vectors, these 2 vectors. And again, those are vectors whose length is less than 1. And then I have, I'm in the numerator. So anyway, when we multiply the lengths of those vectors, and do 1 divided by that. That's going to give us a value greater than 1. So it takes us up to 5 dB. And then as that point moves around the unit circle and we approach this pole, again, that pole is pushing the response up. And so at that frequency, we're going to get a peak. And then as we move around the unit circle, the length of the vector from the pole to the point in question increases. So when we multiply that and put it in the denominator, the response actually decreases as we move away from the poles. So we get a magnitude response that looks like this picture. So that's what's happening in terms of the magnitude response. There's a lot to keep track of in your head as if you want to think about the magnitude response in this way and sort of visualize what that would look like based on the pole zero diagram. But if you look at a lot of these, and we'll look at more of them further ahead, you can start to get a sense for what the magnitude response would look like just by visualizing the pole zero plot. All right, let's move on now and look at phase for the same system. Now, again, so what I've written here is we have the same transfer function. The frequency response I've written as shown here. And now what we're going to do is think about taking the phases of these different pieces. So it's the same set of vectors as before. You can see that the phases, though, are the angles those vectors make with the positive real axis. So, okay, so for the 2 poles, we're going to have this angle right here, and then this angle going around to the conjugate pole location. So we've got a little angle and a big angle. So we're going to have the sum of those 2 angles, and then the zeros contribute this other angle that's shown here in blue that goes around to the 0 vector, the vector that points from the 0 to the point on the unit circle in question. And so the phase response is the sum of the 0 vectors minus the sum of the pole vectors, the angles of the pole vectors. So we have these angles minus these other angles. And then the phase response is basically illustrating for us, showing us what happens to those angles and the sums of, and differences of those angles as the point in question moves around the circle. And I've included here a plot of the phase response. You can imagine what the group delay would look like because it's the derivative of the phase response. So here you're going to have a large delay at these 2 points where the slope is steep, and then at other points where the slope is not as steep, the delay wouldn't be as dramatic. So that's the phase response. Again, for phase response, there's a lot to keep track of in your mind as you move around the unit circle. So typically, we instead of doing this analysis using angles and so on and magnitudes, we just let a computer do the calculations for us. I want to step over now and look at just an example, because what we've done so far is look at individual poles and zeros and the responses that they contribute. We've also now looked at how multiple poles and zeros contribute to the magnitudes and phases. And in this example, what I want to do is just let you imagine how if we have many poles and zeros, as you can see in this example, the pole zero diagram is shown at the bottom of the page. If you had many poles and zeros, what would that do to the response? Remember, each one of these poles or pole pairs, conjugate pairs, is contributing to both the magnitude and the general way the magnitude is shaping up, and also the phase and the group delay. But when you have as many poles and zeros as you see here or more, it becomes tricky to keep track of what's going on in your head. But in general, there are some things we could say in general. If we look first at the magnitude response, notice that for low frequencies, which are going to appear over here on the right side of the unit circle, the magnitude, we're passing some zeros. We're passing through some zeros which appear like they're on the unit circle. And so the response should be very low here. And also at high frequencies, the response is going to be low because we have zeros on the unit circle over near -1. Whereas at mid-frequencies, we're near poles, and so these poles are going to push the frequency response up. And if we look at the magnitude response, we can see that this is the case. At low frequencies and then here at high frequencies, the magnitude response is 0 or small. And you can see how small if you look at the magnitude response in dB. We're down about 60 decibels for low frequencies and high frequencies. And you can see there is a passband at these mid frequencies near the poles where the response is close to 1. The other thing I find interesting is notice that we have a 0 at 1, that's DC, and then there's another 0 on the unit circle at a very low frequency. And then as we move to high frequencies, we're going to have another null and another null at the highest frequencies. And you can see those nulls out here in these ripples. So here's DC, and that other little 0 right here and here, that's giving us these nulls in the response out here. And then these 3 zeros, those are giving us these nulls, 1, 2, 3, out here at high frequency. And then you could count the ripples in the passband and relate that to traveling around the unit circle, passing close to these poles. Similar sorts of comments could be made about the phase response and the group delay. That's coming about, these peaks in the group delay, that's coming about because we're passing by these poles. And as we do so, we're going to experience group delay passing through there. So that means if you have sinusoidal components in the input signal near these frequencies, those are going to experience a large delay. Whereas frequencies over here are going to experience very little delay. So imagine taking responses like these and combining multiple responses like these to build up the response for a more complicated filter like a bandpass filter as shown here. All right. Now we're going to change gears for just a minute. I want to introduce you to a couple of different kinds of systems because this illustrates some ideas. The first being Allpass systems. So here I'm showing you the transfer function. You can imagine what the difference equation would look like for this. But here's the transfer function for an Allpass system. You can see that we have a 0 at A inverse conjugate, and then there's a pole at A in the complex plane. And the thing that I want to point out here is we call this a conjugate reciprocal pair of poles and zeros. So we're going to refer to this as a conjugate reciprocal pole zero location. If you look at where these fall in the complex plane, if we have a pole at A, the conjugate reciprocal location is on the same ray emanating from the origin, but it lies outside the unit circle at the reciprocal magnitude location. So again, A has a magnitude less than 1, and when you reciprocate that magnitude, A inverse conjugate will have the reciprocal magnitude outside the unit circle. So that's what happens for a single pole and 0. The reason these are called Allpass systems is because if you take the magnitude of the frequency response, you will see that the magnitude is 1 for all frequencies. So we call these Allpass systems because you put a signal in and all of it comes out the other side, with no change in the magnitudes, but the phase is altered as a function of frequency. And I've plotted here the principal value of phase and also the group delay for 2 different pole locations, one being on the real axis at 0.9, the other on the real axis at -0.9. And so you can see at 0.9 we get a delay of about 20 samples, and at -0.9 that would be for low frequencies, and for the pole, or I'm sorry, the 0. Well, actually it's the pole. The pole at -0.9, the delay is at high frequencies. So again, if the pole location is at 0.9, the 0 would be located at the reciprocal location, which is 1 over 0.9, which is about 1.111. If you have complex conjugate pairs of poles occurring inside the unit circle, you're going to have a pair of conjugate reciprocal zeros appearing outside the unit circle. So if you have a transfer function that includes poles on the real axis, they would have this form shown in the first set of terms. And then if you had complex conjugate pairs of poles inside the unit circle in an Allpass system, that would give rise to this second piece here. M sub c being referring to complex conjugate pairs of poles, M sub r being real poles. So you can put a bunch of poles and zeros together and create all kinds of Allpass systems. They all have unity magnitude response. They differ in their phase responses. And so by cascading these with other systems, it allows you to compensate for non-ideal phase responses and group delays. So often they're used as compensators. In this pole zero diagram, you can see that this pole is at the location -3/4, and there's a 0 at -4/3. Here's a pole at 1/2, so there's a 0 at 2, and so on. Then here's a pair of complex conjugate pairs of poles, and the zeros are located at conjugate reciprocal locations outside the unit circle. So again, A inverse conjugate lies on the same ray as A, has the same phase. All right, so that's a little bit about Allpass systems. We'll look at some examples of those in a few minutes, but I want to turn attention to talking briefly about minimum phase systems. If you watched the Z-transform video, I mentioned this briefly there. First, let's review a couple of principles. First of all Allpass systems, as we've just seen, have unity gain, and the poles and zeros occur in pairs at conjugate reciprocal locations. Minimum phase systems have all their poles and zeros inside the unit circle. So immediately you see that Allpass systems are not minimum phase because they have a 0 outside the unit circle. But minimum phase systems have all poles and zeros inside the unit circle. Why is this important? Because if you take the inverse of a minimum phase system, remember when we invert, poles and zeros trade places. So zeros in a system become the poles of its inverse and vice versa. So if you have so minimum phase systems have a causal stable realization, and their inverse is also causal and stable. So this is good because if you have a minimum phase system which distorts a signal and you want to undo that distortion, you can do that for minimum phase systems just by using a causal stable inverse transfer function. So that's very good. But in general, most systems that you encounter in the real world are not minimum phase. And so we would like to understand, well, to what extent can I compensate for the non-minimum phase characteristics of real systems? And here's an answer to that, or at least one way to answer the question. So it turns out that an arbitrary transfer function h of z, well, I should say a rational transfer function h of z, which corresponds to a linear time-invariant system, can be decomposed into a part that is minimum phase, where all poles and zeros are inside the unit circle, and a part that is Allpass, where poles and zeros appear in these conjugate reciprocal pairs. So this is a decomposition of a transfer function. Now, let's suppose we've taken out this decomposition. We could multiply both sides by the inverse of the minimum phase portion, so that on the left we have a cascade of the original system with a new system that we designed. This is the compensator that's compensating for the non-ideal magnitude distortion of the system. When you do that, it leaves behind some residual distortion, but that distortion is limited to the phase because remember, an all-pass system has unity magnitude response. So what this does is it compensates for any non-ideal gain characteristics, but it leaves behind some all-pass characteristics, which again might be okay, but it might not be okay. So this shows the cascade of the original system, which maybe is a distorting, it's doing something you don't want to a signal. And here is our compensator. It's the inverse of the minimum phase part. The cascade of these two together is an all-pass system. So again, this does no magnitude distortion. It leaves behind only phase distortion, which again could be okay or maybe not. The question is, how do we perform this decomposition into a minimum phase and an all-pass part? To think about this, what I'd like to do is, let's suppose that our transfer function h of z, which we'll assume is known, has 1, 0 outside the unit circle at a location z inverse or c inverse conjugate. So what we're doing is we're going to figure out, how do I compensate for 1, 0 outside the unit circle? And then if there are many, you can apply this procedure iteratively to compensate for all those zeros outside the unit circle. So let's suppose that we've applied this process and that there's only one remaining 0 outside the unit circle, and it's at the location C inverse conjugate. You can see that if I plug C inverse conjugate in here for Z inverse, the inverses disappear and I have C conjugate minus C conjugate. So that is indeed a 0 of the system. So to compensate, what we're going to do is we're going to multiply and divide by 1 minus CZ inverse. So here you see that appearing in the multiplication here in the numerator and also multiplication in the denominator, but I've collected the terms in a particular way, as you see here. And the reason is because when we look at what's in parentheses, we recognize, oh, that is an all-pass system. And this piece right here, C, is a 0 that lies inside the unit circle. So essentially what we've done is we've introduced a 0 inside the unit circle and a pole inside the unit circle, so that pole and 0 actually cancel each other. But the location where we've introduced that pole and 0 is at the conjugate reciprocal location of the offending 0 outside the unit circle. Let's take a closer look at this with some pictures now that we've talked through that. Okay, so let's suppose that this pole 0 plot over on the right-hand side shows us where the poles and zeros of the original transfer function lie in the complex plane. And as we've discussed, we have 1, 0 that lies outside the unit circle. Because of that, this system is not minimum phase. So what we're going to do is we're going to introduce a 0 and a pole at the location C, and that location is inside the unit circle at the conjugate reciprocal location. So again, it's on the same ray as the bad 0, and then we're going to keep the pole lumped with the 0 outside the circle. That forms an all-pass system. And then we're going to take the 0 and we're going to lump it with all the other poles and zeros lying inside the unit circle, and we've accomplished our objective. Notice that the poles and zeros for the transfer function here on the left is minimum phase. This is minimum phase. The other part is all pass. And so what we can do, if h of z is performing some kind of distortion, we can remove all of the distortion from these due to these poles and zeros, leaving only an all pass distortion. I say here that the same process can be applied to poles outside the unit circle, but with poles it's a little bit different because poles outside the unit circle lead to unstable causal realizations. So, but they correspond to anti-causal stable realization. So anyway, there's some issues that we have to think about if we want to think about applying this process to poles. But assuming that we have a stable system to begin with, you can turn it into or decompose it into a minimum phase part by reflecting all the zeros inside the unit circle and then lumping all of the poles that show up as we reflect those into the circle, lumping that into Allpass components, which again are stable because they have poles inside the unit circle. And anyway, so this gives us a decomposition. Remember, you can compensate for the minimum phase part of the distortion. So I wanted to introduce the ideas of Allpass systems and also minimum phase systems in passing here. That's a little bit of an aside. Let's go back to some examples. And I've done a bunch of examples here in MATLAB. I want to show these to you. We're going to start by looking at single pole Allpass systems. We're going to look at Allpass systems with a pair of complex conjugate poles. Then we're going to look at a DC blocker, an FIR low-pass filter, and IIR low-pass filters. And for each of these, we'll look at the magnitude response, phase response, group delay, pole zero plot, and the impulse response. So here's the first example. This is an all-pass filter with a single pole on the real axis. You can see in the pole zero plot down here at the bottom, I have a pole inside the unit circle, a zero at the conjugate reciprocal location, and as promised for all-pass systems, the magnitude response is a constant. It's equal to 1, which is also 0 dB. The phase response has the shape that you see here. Again, the reason it has this response is because here we're passing around a pole and on the inside of a zero, and so that's giving us kind of a steep response right there, and then it flattens out at higher frequencies and gets steep for low frequencies. And so that's giving us this group delay behavior that you see here. The impulse response is, I'm not going to say much about it, it's just plotted as a point of interest. Now let's change to a pair of complex conjugate poles for an all-pass system. Each pole has a zero, corresponding zero, outside the unit circle at the conjugate reciprocal location. Again, as promised, the magnitude response is flat. The phase response has the shape you see here. For each pair of pole and zero, we get this steep part of the phase response, and you get at each of those a large delay in the response. Let's look at a DC blocker. What does a DC blocker do? Well, it cuts out DC. If you're sampling a signal and for some reason there's a bias in the voltage that you're sampling, the discrete time sequence will be riding on a DC component, and it's often useful to design a filter to remove that component. And a DC blocker is a simple way to do that. You can see that a DC blocker has a zero right on the unit circle, and then it has a pole just inside the unit circle. So what happens, what that does is that zero on the unit circle pulls the response, the magnitude response, down to zero or towards negative infinity at low frequencies. And then that pole it allows the response to get pulled back up as you move away from DC. And this example shows the pole at 0.9, and then as we move the pole deeper into the unit circle, farther from the unit circle, you see that notch at DC opens up and becomes wider. The ramifications for this could be pretty serious, because if you have signal components that you want to keep at low frequencies above DC, you can see that a pole at 0.5 is just not going to work because it's attenuating low frequencies. But if we go back to the pole at 0.9, it's not attenuating very many low frequencies. All right, now you can apply the same principles to notch out other frequencies as well. Another thing that commonly happens in real applications is, at least in the United States, where our power generation is based on a 60 hertz or harmonics of 60 hertz, you often, when you sample a signal, will find that you have a hum at 60 hertz in your data. So one of the things that people often will do is design a notch filter that notches out 60 hertz. So if you assume that the data is sampled at 500 samples per second, the notch is going to be at, the angle of the notch would be at 2 pi times 60 over 500. That's the angle. And here we're going to have the pole radius at 0.9. So what we're doing is we're putting a pair of zeros on the unit circle at that angle. That's going to pull the response down to 0. And if we put but it'll pull a lot of other things down to 0. So if we put a pole just inside that 0, again, because the pole is inside the unit circle, the system has a causal stable realization. You can see the stability here in the impulse response, the fact that the impulse response decays as you move out towards positive infinity. You can see that here in the linear or the dB magnitude response, we're notching out 60 hertz. And that's with a pole radius of 0.9. Here's a pole radius at 0.99. You can see that the width of the notch changes quite a bit as you move that pole out to the unit circle. And so where you want to place that pole just depends upon what other kinds of frequencies near 60 hertz that you want to preserve in the output. Notice also that it affects the phase response rather dramatically. Notice here at 0.99, the group delay at the notch frequency is 100 samples, whereas with a broader notch, the group delay is only about 9 or 10 samples. So all of these things have to be taken into account when you're designing a notch filter. All right, now let's talk about low-pass filters. I'm going to show you a variety of different low-pass filters, all designed with basically the same specification in mind. These will pass low frequencies, which again appear near 0 and near 1. This is the low frequency region of the frequency axis, and then up near 0.5, this is the high frequency region. So we're passing low frequencies and stopping high frequencies. And you can see that when you look at the dB response, those highest frequencies are really getting pounded down. This plot goes down to negative 70 decibels. So those really high frequencies are really getting hammered. And at low frequencies, there's 0 dB of attenuation. So yeah, not much happening at low frequencies. It's interesting to look at the pole 0 plot. This has 3 zeros stacked up at negative 1. And then the poles are over here near low frequencies. And they're arranged so that we get a nice monotonic response in the pass band and a monotonic response out here in the stop band. This is called a Butterworth filter. It's a third order filter. It's stable. The poles are inside the unit circle. Everything looks good. You can see the phase response and the group delay over here. This is a nonlinear phase response and a nonlinear group or non-constant group delay. But the group delay is not too bad. We have about 4 samples or about 1 sample of delay, somewhere in between there. If we look at a Chebyshev type filter, a third order filter, the response changes a little bit. You can see poles and zeros, and again, as we move around the unit circle and get close to these poles, the response is being pulled down. And over here for low frequencies, the response is closer to the poles than the zeros, and so the response is up. Here's an elliptic filter, third order. Again, the poles and zeros now are spread out a little bit more rather than being stacked up in one location. Similar sort of behavior from the perspective of the pole 0 plot and the magnitude and phase response. The next example is an FIR filter. It's what's called an equi-ripple filter because the ripples in the pass band and the stop band, you can see the stop band here, have equal amplitudes. And if we zoomed in on the passband, you would see that it has a ripple behavior where the amplitude of those ripples are equal in magnitude across the passband. Whereas the IIR filter examples used a low-order filter, a fairly low-order, third-order filter, to achieve a similar kind of low-pass filter characteristic with an FIR filter, finite impulse response. We would need to use a much higher-order filter. This is a great filter, by the way, though. If you look at the stop band attenuation, we're down below 70 decibels of attenuation in the stop band. It's a pretty good filter. Anything that we intend to stop is being really pounded down by this filter. The pole zero plot looks very interesting. Notice that the zeros in the stop band are on or close to the unit circle, and the zeros are away from the unit circle in the pass band. The poles are all stacked up, all 42 of them are all stacked up at the origin. So the poles are tending to push the frequency response up. These zeros close to the unit circle are pulling the response down, and then the zeros away from the circle are not pulling it down as much. They're basically compensating for what the poles are doing out here in the passband region. The important thing to notice here, if you think back through all these other examples, let's just quickly flip through these other examples again. I want you to look at the linearity of the phase and the constancy of the group delay. So here we are back with our all-pass filter. The phase is nonlinear, the group delay is not constant. Again, nonlinear, not constant. I'm looking at these two charts, phase response, the unwrapped phase, and the group delay as we step through these examples. Nonlinear phase, non-constant group delay. Nonlinear phase, non-constant group delay. The same story plays out again and again for all the IIR filters. But when we get to the FIR filter, notice that we have a linear phase response and we have a constant group delay. What this means is that all the signal components at all the different frequencies passing through this filter will experience the same amount of delay. So things that go in will come out time aligned. So the components that go in will come out with the same amount of delay. So if there's important things to consider about time alignment in signal components, FIR filters can preserve those characteristics. The other thing to notice is that whereas if you go back and look at the impulse responses for these other IIR filters, there's absolutely no symmetry whatsoever. Whereas when we get to this FIR filter, notice that we have a symmetric impulse response. And it turns out that we will see that when you have this symmetry in the impulse response, you can have linear phase and constant group delay. Going back and looking at this again, we've seen this example before, but where we had nonlinear phase and non-constant group delay, and we saw what that could do. We had signals on the input which were time aligned with a certain ordering get reverse ordered in the output signal when you have a nonlinear phase response. When we have systems with generalized linear phase, which is what we're going to start talking about now, this is not going to happen. What do generalized linear phase systems look like? Well, you can see here at the bottom of the page, I'm presenting a frequency response, and I'm representing it here in a particular way. Let's suppose that the frequency response is equal to a real bipolar function, A of f, times a complex exponential, e to the minus j 2 pi f alpha plus j beta. And if you look at the phase response of this system, well, first of all, let me back up. What is a real bipolar function? A bipolar function, a real bipolar function is one that takes on only real values. So A of f is a real function. It takes on real values. And by bipolar, I mean that it can be positive, negative, and zero. So that's the bipolar part of it. So what that means is that all of the important phase contributions are coming from this complex exponential, which has a phase which we're going to call generalized linear phase. Here's the phase written out. So again, because A can be positive or negative, the phase is going to be pi times the sine of A of f. So if A of s is positive, the sine would be 0. If A of f is negative, we would put a -1 here, and so you'd have, so this component can contribute either a 0 or a pi to the phase response. So for generalized linear phase systems, the important part is that you have a linear piece, and you have a constant. So that's generalized linear phase. Linear phase, perfectly linear phase, you'd only have this term -2 pi f alpha. So by generalized linear phase, we're allowing there to be a y-intercept. And the beautiful thing about this is that when you have systems with generalized linear phase, the group delay is a constant. Now that could be a very important thing depending on the application. Let's take a look at what would be needed in order to have generalized linear phase. So here is an example of an ideal low-pass filter. So again, it has a gain of 1 in the passband, which is frequencies below FC for cutoff, and it's 0 for frequencies above the cutoff frequency. And down below here, I'm showing the impulse response, and I'm also plotting the impulse response over here on the right-hand side. You can see that for a zero-phase filter, an ideal zero-phase filter is going to have a non-causal impulse response. So we have, it's a sinc function, and we have these tails decaying as we move off towards positive and negative infinity. Here the cutoff frequency in this example is 0.1 cycles per sample. Now let's take that frequency response and modify it by adding in a linear phase piece. So instead of a gain of 1, we have a gain of e to the j 2 pi f alpha. Now if you look at the magnitude response has not changed because this is still the magnitude response. But what this does is it modifies the phase response. So here, if I factor out the e to the minus j 2 pi f alpha, we have a real bipolar function times an e to the j piece. So this function has the form of generalized linear phase. And when we do the inverse Fourier transform to calculate the impulse response, we get a sinc function, but now it has a delay of alpha. So when we multiply in the frequency domain by e to the minus j 2 pi f alpha, in the time domain, that gives us a delay of alpha. This is just the time delay property of the Fourier transform, really is what's going on here. For nonlinear, I will remark that for nonlinear phase systems, well, never mind, I'll cancel the remark. So notice that the impulse response is just modified by the group delay. Let's continue on with this example, and I want to take a look at a couple of different cases. And now what we're looking at, focusing here on, is the symmetry of the impulse response. Again, what we're trying to do is distill, what does this generalized linear phase notion imply about the impulse response? This is going to be important to us because soon we're going to be designing filters. And if I want to design a filter that has constant group delay, which could be a good thing, could be an important thing, I need to understand how to do that and what would that imply about the impulse response. Okay. So with that as background, let's take a look at a couple of different examples. Let's take alpha equal 5 for this ideal low-pass filter that has a sinc function as its impulse response. If we delay the sinc function by 5 samples, we're going to get a sequence that looks like this that you see here on the right. And if you focus in now on the symmetry of the impulse response coefficients, notice that at 5, we have, at n equal 5, we have a number. But then at n equal 4 and 6, which are one sample ahead and behind 5, we have the same impulse response value. And then at 3 and 7, 2 samples ahead and behind alpha, we have the same value. So you can see that we get this even symmetry. I say odd here, but I'm going to say even symmetry about the point alpha, or about n equal alpha, or n equal 5. Now let's change alpha, and let's say alpha is equal to 4.5. And if we go through that same process again, 4.5 is not a point in the sequence like 5 is, but we could still talk about symmetry about that point. So here we have samples 4 and 5 are equal, and samples 3 and 6 are equal, and so on. So we still have this even symmetry about the point alpha, even if alpha is not in the sequence. Well, now let's try alpha equal 4.3. Now if we look at this impulse response, there is no symmetry taking place here. The thing that I want to distill from this is that if alpha is equal to an integer, we get symmetry. If alpha is equal to an integer plus 1/2, we still get symmetry. But if alpha is equal to an integer plus something other than 1/2, some other fraction, then there in general is no symmetry. Based on these ideas, we're going to define 4 different classes of generalized linear phase systems. Types 1 through 4, we'll refer to them by their numbers. And there are 2 different symmetries, even and odd, and there's 2 different values for the order of the impulse response, and that is even and odd as well. So let's talk about the order here for just a moment. So these are going to be finite impulse response filters, and so the impulse response, h of n, is going to take on, well, we would say that the region of support, I mean, it could take on 0 values over this region, but in general, the impulse response values are going to be from 0 up to m, and this is, let me show you an example. Why do we call it m, which is the index of the last impulse response coefficient? Why do we call that the order of the filter? Well, focus on this here for just a minute. Here I have a finite impulse response filter, h of n, and its z transform written out. If you just write this out, you get h0 times 1 plus h1 z to the minus 1 plus h2 z to the minus 2, and so on, out to hm z to the minus m. This is a polynomial, and the order of this polynomial is m. It's a polynomial in z to the minus 1, but the order of this polynomial is m. So we would say that this filter, which is an FIR filter, has order m. What's the length of this filter? How many coefficients does it have? That's something else. That's m plus 1. So the length of the filter and the order are different by 1. The length is 1 more than the order of the filter. So with that as a background, and written out here on this slide, there's 4 cases. We can have even symmetry about the point alpha, which is m over 2, and we can have an even or an odd order. There's 2 variables, so there's 4 cases. So cases 1 and 2 have even symmetry about the point m over 2, and the order could be either an even integer, in which case m over 2 is an integer, or it could be an odd integer, in which case alpha, which I've denoted here as a, is an integer plus 1/2. This harkens back to these ideas here. So we want alpha, which is m over 2, half of the order, to be either an integer or an integer plus 1/2. So we can obtain this if the order, which is 2 times alpha, is always constrained to be an integer. So the order will always be an integer. It can't be a non-integer. But it will always be either an integer, so half of the order will either be an integer, if m is even, or an integer plus 1/2 if m is odd. And then we could, the other cases 3 and 4, we have odd symmetry in the impulse response. And the order could be either even or odd in that case as well. Now notice this expression for the impulse response here. H of n equal h of m minus n is the way we're going to describe the symmetry. So when you put h or n equals 0 in this says that h0, the first coefficient in the impulse response, is equal to hm, which is the last coefficient in the impulse response. If I put n equal 1, then I have h of 1, the second coefficient in the impulse response, equal to h of m minus 1, the second to the last coefficient in the impulse response. So you can see that this is how the symmetry is described correctly in every case. We don't need alpha to describe the impulse or the symmetry. We'll just describe it in terms of m, capital M, the order of the filter. Now, in these different cases, this leads to implications about the frequency response and its this bipolar function A being real and even or being real and odd. And it also leads to implications about beta. Again, we're not going to go through all the math of this here, but for cases 1 and 2, beta will be either 0 or pi. For cases 3 and 4, beta will be pi over 2 or 3 pi over 2. Okay, so these are the 4 different kinds of filters. I want to drill home these ideas a little bit more. So for type 1, we have an even order, so an odd length, the 5 coefficients here in total, but it's an even order. And the delay, alpha, is going to be m over 2. This is the group delay. So it's a symmetric, it's even symmetry about the point m over 2. The center of symmetry is here, m over 2. And m over 2 will be the group delay. This is going to be a linear phase. We can guarantee the phase will be linear because of the symmetry. And when you take the derivative of the phase, that's going to give you a constant because it's a constant slope for a line. And the slope of that line will be m over 2. For type 2, we have an odd order, so an even length. And the center of symmetry is not a point in the sequence, but we can still talk about even symmetry about that point. So the first coefficient and the last coefficient are equal. The second coefficient and the second to the last coefficient are equal, and so on. Types 3 and 4, we have, instead of even symmetry, odd symmetry about the center of symmetry in the sequence. And we have 2 examples here where the order is even and where the order is odd. Let's take a look at some other implications of these facts. Again, you can read about the details of this in the textbook, and I encourage you to do so. I'm just not going to talk about it in these lecture videos. So here we're looking at both the impulse response and its symmetry. We're looking at the magnitude response. We're also looking at the pole zero plot. Remember, these are all FIR filters. So the zeros are shown here in the pole zero plots. The poles are all located at the origin and they're not shown. So we have types 1, 2, 3, and 4. And I've included a mention of the symmetry of the impulse response and the order of the filter being even and odd symmetry in the impulse response and even and odd orders. Now, for type 1, it turns out that there are no structural constraints on the locations of zeros. But for the other 3 types of filters, there are constraints. For type 1, it turns out that no matter what kind of even symmetric, odd ordered filter you choose, when you take the roots of that polynomial, you will always get a root at -1. And that's what I've highlighted here. What does a root at -1 mean? Well, in terms of the frequency response, it means that there will be a null in the frequency response at high frequency. So, if you want to use a type 2 filter, what kind of filter would this be good for? Well, you don't want to use it for a high-pass filter because it has to have a null at high frequency. But you could certainly use it as a low-pass filter because there's no requirements on zeros being at low frequencies. Type 1 filters have no requirements on the zeros whatsoever. The zeros can appear anywhere. And so I say here that a type 1 filter could be used as any kind of filter. Type 2 is good for low pass. Type 1 would also be good for low pass. Don't get me wrong there. If we move over to types 3 and 4, they also have structural constraints. When you take and root an odd symmetric polynomial with even order, you're guaranteed that there will be zeros at -1 and 1. What does this imply about the frequency response, the magnitude response? It means that there is guaranteed to be a null at 0 frequency, 0 and 2 pi, that's the same point, and a null at high frequencies as well. That comes from the 0 at -1. The 0 at +1 gives rise to these nulls in the magnitude response at 0 and 2 pi. That's just going to happen. So what kind of filter would this be good for? Well, you could certainly use it to design a bandpass filter. That's essentially the filter that you see pictured here. You could also use it for a Hilbert transformer, which passes through 0 at these frequencies as well. And we've actually seen that in one of our programming assignments where we designed a Hilbert transformer. The frequency response had that, and the impulse response had that odd symmetry. Here's a type 4 filter. It has a structural requirement for a 0 at DC, as you see here in the magnitude response. And so again, you could not use this for a low-pass filter, but it would make just a fine high-pass filter, or perhaps a differentiator as well. So here's a few thoughts on filters and the types and what you should use them for and what maybe you shouldn't use them for. Let's continue this idea exploring where the roots must be for polynomials whose coefficients have these special symmetry properties, where the first and the last coefficient are the same, and the second to the first and the second to the last coefficient are the same, or the negatives of each other. So again, we could have even symmetry in this polynomial, odd symmetry in the polynomial. The polynomial could have an even order or an odd order. But generally, we can make the following statements about the locations of the zeros for these kinds of polynomials. So first of all, for roots at general locations in the complex plane, and that'll become a little bit more clear as we go through the list here, but at roots in a general location in the complex plane, those roots will appear in a foursome. So if you find a root at z, you will also find a root at z conjugate. And you'll also find a root at z inverse. And you'll also find a root at z inverse conjugate. We know a little bit about the locations of these roots. The locations of a conjugate pair are pretty obvious. They're at reflected points across the real axis. And z inverse conjugate is on the same ray as z, but it appears outside the unit circle if z appears inside the unit circle. The same is true for z inverse being the reciprocal conjugate of z conjugate. So you will not find for a filter with real coefficients and the symmetry structures we've talked about, the roots will pair up in foursomes, or if they're in a general location, or if those roots happen to be on the unit circle, then they will pair up in pairs. So if you find a root at z, you'll also find one at z conjugate. If the roots happen to fall on the real line, they will also pair up at reciprocal locations. So if there's a root at z, you'll find one at z inverse. And then it's also possible to have roots appearing at plus or minus 1 all by themselves. These are the only kinds of roots that can appear alone. All other roots will appear in pairs, as reciprocal pairs on the real line, conjugate pairs on the unit circle, or as foursomes in general locations. Let's take a look at those 4 types of filters again and see some examples. So over here I'm highlighting a 4-tuple. Again, this is we find a root at a general location, not on the real axis, not at plus and minus 1, not on the unit circle. And so that root will appear with 3 other pairs, one at a conjugate location, one at a conjugate reciprocal location, and one at a reciprocal location. Where else do we see that in these pictures? Well, here's another example right here. That 1, 2, 3, 4, that's a foursome. Here's another one. 1, 2, 3, 4. That's a foursome. Here are 2 more foursomes. 1, 2, 3, 4. 1, 2, 3, 4. What else can happen? Let's look and see if we can find a unit circle complex conjugate pair of zeros. And that appears right here. So here's a 0 on the unit circle, and so it naturally will have to have a partner at the conjugate location. Where else do we see this? I see it here and here. I also see it here and here. Root on the unit circle, and it will have to have a conjugate pair. Where do we see reciprocal pairs? That's any 0 on the real line. So here's a reciprocal pair. Here's a 0 on the unit circle, not at plus and minus 1. So it must also have a reciprocal pair. Here's one, and it's reciprocal. Here's one, and it's reciprocal. Then we can have zeros at plus or minus 1 appearing alone. Where do we see that? Well, here's one. Here's one. Here's one. And then over here we have another one, another example of that. Again, all the poles are at the origin, and these rules will be followed. If you have a symmetric or an anti-symmetric, an even symmetric or an odd symmetric impulse response, whether it's even ordered or odd order, the 0 locations, the roots, will appear in these locations as described here. The other thing to notice is that in all of these examples, there are necessarily poles, zeros outside the unit circle or on the unit circle. So none of these examples, none of these FIR filters that we'll design that have the symmetry properties will be minimum phase. All right, so the next topic then is to go design some filters.